This will be the last lecture over mass spectrometry. I think I may do one more. So we'll just talk about the different kinds of instruments. So again, for a mass spectrometer, you have an ionizer. That's the first part of the instrument. And once this sample is ionized, then it goes through a mass analyzer, and that's basically the heart of a mass spec. So that's where the ions are separated based on their mass. And then it goes to the detector. So far we've talked about the electron impact ionizer and the magnetic sector mass analyzer. So in this lecture we'll talk about 3 different types of way to ionize your compound. So that's basically right, just to get it into a charged state, so that the electric fields in the mass spectrometer can accelerate the ions through the mass analyzer. And then in this lecture we'll talk about how quadrupole works as well. Okay, so regarding the electron impact, so it's good for molar masses less than 1,000, so relatively small molecules. So it has some limitations to it. So some of the limitations, so the molecule must have a vapor pressure of at least about 10 to the minus 6 torr at its highest stable temperature in order to get the sample into the mass spectrometer and into the gas phase. And another limitation is that you use about 70 electron impact. You need about 15 electron volts to remove an electron. So if you hit the molecule with a 70 electron volt electron, that imparts a lot of energy to the molecule. So the molecule, once you knock the electron off, the molecule is left with a lot of extra energy. And how does it dissipate that energy? That can lead to fragmentation of the parent peak. So you get, and those fragmentations are very rapid, so anywhere from 10 to the minus 10 to 10 to the minus seconds. So for example, if you had an original molecule ABC, and let's say it had a molar mass of 100 grams per mole, so once you knock an electron off of the molecule and it becomes ABC and becomes charged radical cation, has a lot of extra energy because you just bombarded it with high energy electrons. And so that molecule may not live long enough to hit the detector. It may fragment extremely fast. And if it fragments really fast, then you don't see a peak at 100 anymore. You just see a bunch of fragment peaks. And so information can be lost. And so usually that's one of the things chemists would want to know is what is the molar mass of your compound. So if your molecule doesn't live long enough to hit the detector, that's a problem. So it would be ideal to impart less energy to a molecule to ionize it so that you could minimize fragmentation. And that's again important if you want to observe the parent ion peak and study the parent molecule. It's got to live long enough to hit the detector. So that's where some of these other ionization methods come into play. So the ionization method number 2 that we'll look at are what are called desorption methods. And so we'll look at 2. We'll look at what's known as FAB and MALDI. So FAB is just an acronym that stands for fast atom bombardment. And MALDI is an acronym that stands for matrix assisted laser desorption ionization. So they're just 2 different ways to get your molecule ionized in the gas phase. Okay, so these are primarily used for large non-volatile molecules or ionic compounds. So basically what you have is what's called a matrix. And you have your molecule embedded in the matrix. And then you hit your molecule with energy, and that causes your molecule to desorb from the matrix and go into the gas phase, right, as an ion. And then the electric fields in the mass spectrometer can be used to accelerate that ion into the mass analyzer. So there are some disadvantages to this. So the samples may not be efficiently ionized or desorbed. So your sample is not used efficiently. So that means you have to maybe use more of your compound because it may not be desorbed efficiently. So that's a problem if you can only synthesize a little bit of it, or if you only have buy a little bit of compound to study, or if your compound's really expensive, you don't want to waste much of it. And so the information is more limited than what you would get with Electron Impact. Why is it more limited? Because in these methods there's usually no or very little fragmentation. And so when your molecule breaks apart into smaller pieces, if you can figure out what those pieces are, then you can use that to get structural information about your molecule. So if you don't happen to know what your molecule is, and all you get is a mass, because there's no fragments, then you've lost information. And furthermore, the spectrum may be complicated by the matrix itself, because the matrix is an organic molecule. And so that could get into the gas phase and get into your mass, well, we'll get into your mass spectrometer, so you're going to see peaks for your matrix as well. But they are very good methods to observe the parent ion peak. Right, because it's lower energy ways to get your compound into the gas phase and ionize, so the may not fragment. Okay, so the basics of how a fab works. So if you have ionization sources, fab, the mass analyzer can vary, and we haven't talked about detector at all yet, and we probably won't. So basically what happens is you have what's known as a fab gun. So an element that can basically produce a beam of electrons, and you basically shoot that beam of electrons at a gas supply. So the gas supply is typically argon or xenon, or it could be cesium. And basically what this is going to do, it's going to produce a beam of fast-moving xenon or argon atoms, or cesium will be ionized in the process, and then you create a beam of cesium cations. And then you basically direct that beam of xenon, argon, or cesium cations towards your sample. So what you have in this case then is you have your sample. So M is your sample, M meaning the molecular ion. Well, it's not an ion yet, it's your molecule. Whether that's a small organic molecule or a big complex organic molecule like a protein. So you would typically take your compound and dissolve it in a very solvent with a very low vapor pressure, high boiling point, such as glycerol. So you got your compound dissolved in glycerol, for example, and it's a droplet on the surface, and then you shoot that beam of argon or xenon or cesium ions towards it, and that causes your molecule to desorb from the surface. And so then your molecule goes into the gas phase. Sorry, just pulling up my notes on my own computer. That's what I'm looking away from the screen for. So your molecule then will typically go into the gas phase, pick up a proton in the process. You know, where does the proton come from? So you often add trifluoroacetic acid to your sample. So take your sample, dissolve it in glycerol, add some trifluoroacetic acid to it, and trifluoroacetic acid is acidic. It's got an acidic hydrogen. So when your molecule desorbs from the surface, it may take a hydrogen from trifluoroacetic acid with it, and so, right, acid H+, so then that basically gives charge to your molecule. So now you have your molecule with an extra hydrogen, so it's one mass unit higher than what it would be, and it's charged. So now that can be accelerated in the mass spectrometer. You know, so or your molecule could come into the gas phase with the sodium ion. Right, where does the sodium come from? Where sodium is all over nature. Right, sodium is a ubiquitous ion. Just tons of sodium all over the place. Sodium in all of your solvents, maybe on the surface of your glassware. So when the molecule desorbs from the surface, it may take a sodium ion with it. So then basically you would have your molar mass plus a sodium. So if your compound had a molar mass of 1,000, then now it has a mass of 1,023 because of the sodium. But the point is it's charged. And now that it's charged, you can accelerate it in a mass spectrometer. So you might also see your molecule minus a hydrogen. So if your molecule loses a hydrogen, for example, if this was your molecule, when it desorbs and goes into the gas phase, it could lose a hydrogen. And so now it's charged. So now it's negatively charged, and that can be accelerated in a mass spectrometer. And so in this case, it would be 1 mass unit less. So if your molecule had a mass of 1,000, now it's got a mass of 999. But it's charged, so it can be accelerated in the mass spectrometer. So FAB is what's known as a soft ionization technique. Electron impact would be a hard ionization technique. So this is a soft ionization technique. It produces mostly intact molecular ion. So that means it's excellent for determining the mass of large and sensitive molecules because you're not going to get fragmentation. So the molecule, once it's ionized in the gas phase, it's going to live long enough to hit the detector. So FAB is good for molecules up to a mass of about 10 to 20 kilodaltons. So that's 10 to 20,000 grams per mole, so very large molecules. Whereas electron impact is typically only good for molar masses of around 3,000 grams per mole, but typically you only use for molecules of about less than 1,000 grams per mole. So that limits you a lot in terms of the molecules that you can study. So the disadvantages to FAB, it requires a more skilled operator to run the instrument and to do that type of experiment. And you have to prepare the matrix, and again you lose some sample because not all of your molecules desorbed from the matrix and makes its way into the instrument. And there's no database to compare to since there's no fragmentation. Right? So whereas electron impact, so when the molecule breaks apart into smaller pieces, that's like a fingerprint of the molecule. If you do the electron impact using the exact same conditions, the molecule should fragment the same way. And so when you see these peaks for fragmentation, so if this is your molecular ion peak, and these are your fragments, that's like a fingerprint of the molecule. And so there's huge databases for molecules where their electron impact mass spec has been published. Right, so over 400,000 different compounds has their electron impact mass spec in a database. So you can compare the databases, and if you have an unknown sample, you can figure out what your sample is based on the electron impact mass spec. But that's not going to be available for FAB or MALDI or ESI, as we'll see, because they typically don't lead to fragmentation. Okay, so how does MALDI work? So this is a technique that was discovered in about 1985. The advantages, again, you can analyze very sensitive molecules like DNA, proteins, sugars, lipids. Whereas if you studied those with electron impact, first of all, they may have too large of a mass. And second of all, as soon as they're ionized, because of all of the extra energy, they may fragment and you may never see the parent ion peak. So the way it works basically is it's based on a UV laser. And so again, you take your molecule and embed it in a matrix and then hit that with a laser, and that will cause your molecule of interest to ionize and go into the gas phase. So you get a hot plume that comes out where your molecule may pick up a proton and be positively charged that way, or your molecule may lose a proton and be negatively charged. And then with the electric fields, to accelerate your ion, and then you can push that into your mass analyzer and separate the ions out based on the molar mass. And so again, you get very little there's very little fragmentation in the technique. So your parent ion for these very sensitive molecules will live long enough to hit the detector. Okay, so basically the matrix, so you have a micron surface of the matrix that absorbs UV, and that leads to ablation of the upper layer, and then that gets ejected into the gas phase. So the matrix is usually one of these three molecules below. So 2,5-dihydroxybenzoic acid, or cyanopenic acid, or 2-cyano-4-hydroxycinnamic acid. So all of these have something in common. They have acidic hydrogens. Right, phenols are acidic, and carboxylic acids are acidic. So they all have phenol and carboxylic acid, so that provides a source of proton in order to get your molecule positively charged. And they all are also absorb UV light pretty intensely, and so that's what so that's where the UV laser comes in. So these molecules are going to absorb that UV light. So they also have a very low molar mass, so that they're easy to vaporize, whereas they're solids, so they have very low vapor pressure as well. So basically, to prepare the matrix, you would dissolve your compound in something like water or acetonitrile. And then you would spot it onto a matrix, to the multiplate, which is basically the crystalline form of one of these molecules. And then your molecule would basically get embedded in the matrix, and then you would load that onto your mass spec instrument, and then shoot a UV laser at it, and then your molecule will absorb the energy from that UV. This heats up intensely, and then it gets ejected as a hot plume into the ionization, into the instrument, and then it gets accelerated by the electric fields. So the disadvantage is time-intensive process. You gotta make the matrix. You get little fragmentation. So again, there's no databases that you can compare results to. And you do get some background interference because these are all organic molecules. They're gonna all be ionized and into the gas phase with your sample. But again, it's an excellent technique if you want to get a parent ion peak that's not going to fragment. Okay, so the third ionization method we'll look at, this is what's known as electrospray ionization. So ESI, electrospray ionization, mass spectrometry, so ESI-MS. So we have this instrument in the A&M Commerce Chemistry Department, so it's about a $400,000 or $500,000 instrument. So these instruments can be pretty pricey as well. But extremely powerful. So ESI is an extremely powerful form of mass spectrometry. So the biomolecule development use led to a Nobel Prize in 2002. So obviously, pretty important technique if it can lead to a Nobel Prize. So it's especially useful for producing ions from macromolecules like DNA, proteins, polymers, any molecule with very large molecular weights. So it's another soft ionization technique. So you're not going to get fragmentation, or if you are, it's going to be minimal fragmentation. And what's even more significant about ESI compared to the other ionization techniques is you can easily get multiple charge states. So you can get your molecule with a +1 charge, +2 charge, +3 charge, +4 charge, plus 10 charge, plus 40 charge. And we'll go through basically how that works. And so you want to keep in mind that mass spec shows output as mass to charge ratio. So if your charge is 40, then the peak that you see actually weighs 40 times than what the output shows, right? If your peak showed your mass was 40, well, it's really 40 times 40 is what the actual mass would be. If the charge on it was 40. All right, so if the charge on the ion is plus 2, and you had a molar mass of 200, then the peak that you would see in the mass spec is 100, right? But you would have to know, if you can figure out that that is really a plus 2 charged ion, then its mass is not 100, it's really 200. Okay, so the fact that it's common to get multiply charged ions greatly extends the mass range of your mass analyzer. And so ESI MS can easily accommodate kilodalton to megadalton molar masses. So 10 to the third to 10 to the sixth, so you can get masses up to 1 million, study molecules up to molar masses of 1 million using an ESI mass spectrometer. And again, the disadvantage is there's little fragmentation. So there's little structural information that can be available. But as we'll see, there are ways around that in an ESI mass spec. Okay, so how does an ESI work? So basically, you take your sample and dissolve it in a solvent, typically water, methanol, acetonitrile, some polar solvent that's volatile. And you may add an acid like formic acid to get a source of proton. And then you draw it up in a syringe, and then you take that syringe and you inject it into a stainless steel capillary. And then the tip of that capillary is kept at a very high potential, and basically you're going to utilize electricity to disperse a very fine aerosol into the mass spectrometer. So you have droplets now. Charged droplets, and those droplets can have a variety of charge. It can be +1, +10, +40. Okay, and so let's go through that. What do those droplets look like in a little bit more detail? So if we take this and expand it and just look at one droplet, for example. So if we have one droplet, so we have your sample in there, so whatever your molecule is that you're studying. And keep in mind, this initial droplet will have lots of those molecules in them. And then they'll have ions in them. They may have protons, extra protons in them, sodium ions in them, potassium ions in them. So this one droplet, for example, it has several of your molecules and several different ions in it. And then what happens is the solvent starts to evaporate. So the droplet gets smaller. Right, so solvent evaporates and your droplet gets smaller. It's still got the same number of molecules in it of your sample, and it's still got the same number of ions in it. You get right. Again, where did the sodium and potassium comes from? They're just all over the place in different solvents, glassware, because they're so ubiquitous in nature. And then H+ could have came from an external acid that you added in the process. Or it could come from, just the solvent itself and whatever minor impurities may be in that solvent. If there's a little bit of water in the solvent, for example. Okay, so as the droplets get smaller, then the charge repulsion starts to build up within the droplet. So more solvent evaporates and the droplet gets even smaller. And at some point, the charge repulsion becomes very unstable. And that droplet will fragment into smaller droplets. So that's what's called a Coulombic explosion. So the one droplet becomes many droplets. Okay, so now we have your molecule and let's just say that droplet only has a potassium and a sodium in it. So let's say it now only has one of your molecules in it and a sodium and potassium, or it only has one of your molecule in it and two sodiums and hydrogen and a potassium and so forth. Or maybe only one of your molecules in it and three hydrogens and so forth. So eventually all of the solvent evaporates off, and then you just have your molecule with whatever ions were left in that droplet with it attached to your molecule. So maybe you get your molecule with two protons, or your molecule with a sodium, or your molecule with a potassium, your molecule with a sodium and a potassium and so forth, or your molecule with just one proton on it, or in this case it's got two protons and a sodium ion. So if we took that droplet, for example, your analyte with three ions bound to it, so it'd show on the mass spec at a third the mass, because it's a 3 positive, it's a +3 charged ion, and if you remember, the mass spec again shows mass to charge ratio. Okay, so let's say you did a mass spec and your compound had a molar mass of 1,000, and these are the things that hit the detector. Right, so what does that look like on the mass spec then? So your mass spec would look something like this. So this would be your compound. Your compound has a mass of 1,000, but it picked up a hydrogen atom, so now it has a mass of 1,001 and it's positively charged, right? Or if it picked up a sodium ion, then sodium weighs 23, so it'd be 1,000 plus 23, so you'd have a peak at 1,023. Or if it picked up a potassium, potassium has a molar mass of 39, so you would have a peak at 1,039. And again, if it only has one of those ions, it's only +1 charged, so you're dividing the mass by 1. So that's the actual compound's mass plus the proton plus the sodium or the potassium. Right, if your compound ended up with two hydrogens and a sodium attached to it, then that would be 23, 24, 25, so that would be 1,025, but it's got a 3 plus charge, so you divide that by 3, and you get 341.7, and so forth, right? Or if you had your molecule with a molar mass of 1,000, it picked up a hydrogen, it picked up a sodium, so then it's 1,024, and then it's +2 charge, so you got to divide that by 2, so that would show up at 512 on the mass spectrometer. Okay, so it's important to keep in mind that these are not fragments. These are the intact parent molecule, simply with different ions bound to them, which thereby changes its mass. By 1 for every hydrogen, by 23 for every sodium, and by 39 for every potassium bound to it. So how does sodium or potassium bind to a molecule, for example? So if you had a molecule that looked like this with a couple of oxygens, where oxygens are partial negative, and so those negatively charged oxygen atoms could coordinate a sodium ion. And so now you would see a peak 23 mass units higher than your molecule with the sodium bound to it. All right, so this is the focus of Dr. Angel's research group, where he examines how proteins bind to metal cations, typically transition metals. So if protein, right, you could have a C-terminal end with a carboxylate oxygen negatively charged, could bind to bind to metal. A thiol, if it's a cysteine, the sulfur can bind to metals. If it's a serine, the oxygen of an alcohol can bind to metals. If it's got a pi system in it, like phenylalanine, tyrosine, the pi system can bind to metals, the pi electrons can. And so, of course, when it binds to metals, it becomes charged, and now it can be accelerated on a mass spectrometer. And then the mass unit, the mass is going to be off by what are the mass of these metals are. Okay, so ESI is very good for compounds that can have multiple charge states like proteins, and you can see anywhere from 0 to 40 charges on the molecule, depending on how many different metals bind to it. So if a Protein had a mass of 100 kilodaltons, but it had a 40 plus charge state. Well, 100,000 grams per mole divided by 40, you would see a peak at 2,500 in the mass spec. So you only need a mass spec capable of, a mass analyzer capable of 2,500 mass to charge ratio to analyze a molecule like that if it's going to pick up so many charges. Okay, so the advantages, again, you can analyze molecules with large masses. There's no matrix, there's just a solvent, so you get minimal background signals, and you can have multiple charge states. So the disadvantages, like the others, there's no fragmentation, but you can address that problem using what's known as ion mobility spectrometry. And you can address the fragmentation issue using what's known as collision-induced dissociation, or SID. Okay, so let's go through how those work. So an ion mobility spectrometry, so you have your ions from your mass spec ionization source, whatever that is. Maybe it's ESI, or maybe it's a different form of ionization. And those go into what's known as an ion mobility chamber. So here, what's in green is you have electric fields, and those are used to accelerate the ion and used to re-straighten the path of the ion out. So your sample comes in, and then what you also do is you bleed in inert gases, such as argon, nitrogen, something that's going to be very non-reactive. So all of these red dots then represent an inert gas. So your molecule comes in and it hits one of these inert gases, and that causes its path to change. And then it hits another inert gas, causes this path to change, and so it doesn't just fly straight through the ion mobility chamber. It flies, like that to the ion mobility chamber, because it's constantly bouncing off of the inert gases. Okay, so which ions will go through the ion mobility chamber faster? Small ions or large ions? Or ions with small cross-sectional area, or ions with large cross-sectional area? Well, obviously the bigger the ion is, the more likely it will be to bump into an inert gas, and that's going to impede its flow. So big things are going to go through the ion mobility chamber slower, and small things are going to be less likely to hit something, so they're going to fly a straighter path, and they're going to go through the ion mobility chamber faster. So you can use that to determine, measure a molecule's cross-sectional area. So you could therefore use that to figure out, for example, how a protein is folded. The more folded it is, the smaller its cross-sectional area is going to be, and the faster it's going to go through an ion mobility chamber. So you can get the three-dimensional shape of molecules like that, for example, or get some information about it. And you can use this for fragmentation purposes as well. So if you get your molecular ion moving really, really fast and you slam it into one of those inert gases, then the energy of collision can lead to fragmentation. So you can have your ESI ionization chamber, and then you can send those things through an ion mobility mass spectrometer, which can cause fragmentation, especially if you do SID. If you get them going fast enough and you cause dissociation, then you can send those through a mass analyzer, and you can separate those ions out, and then you can have a fragmentation pattern for your molecule. So you can get some information about the structure of your molecule that way. Okay, lastly in this lecture, I wanted to talk a little bit of how about, so if we go back, so we've talked about now different ways to ionize your sample and get it charged, and so we've talked about the magnetic sector, so now we'll talk a little bit about how the quadrupole works, which this is what our ESI has. Our ESI instrument has a quadrupole mass analyzer on it. Okay, so this is basically what a quadrupole looks like. You have charged rods. Yes. So charged rods, and then you basically put your ion beam through that charged rod, those charged rods, and that will separate the ions out based on their molar mass. So you have 4 charged rods at the corner of a square, and a constant DC voltage is applied, and then so ions will then basically travel through that box. So just a little bit more. So what is a quadrupole? So you've probably heard of dipole before. So that's an example of a molecule with a dipole. So you have a partial positive end and a partial negative end, and so from the partial, so that would be the dipole with the arrow drawn from the partial positive to the partial negative end. So this would be an example. Benzene would be an example of a molecule with a quadrupole. So benzene, of course, is a flat molecule where it's got high electron density above and below the ring because of the pi system. So partial negative above and below the ring, whereas the carbons in the ring would be partial positive. And so then you have what's known as a quadrupole. So from the ring itself, and draw your arrow from partial positive to partial negative, and so you have what's known as a quadrupole. Okay, so for any given combination of DC voltages applied at the appropriate frequency, right, only ions of a certain mass spec will possess a stable trajectory and will basically fly straight or more straight, and then can pass all the way through the quadrupole. So if we introduce 5 different ions, for example, and so these all have different masses into the quadrupole, and so we have let's say we have the current and the frequency set so that only B plus will fly straight, and the other ions will fly erratic. So A, for example, is going to follow that path, C would follow the green path, D the purple path, and E the black path. And so those are flying erratically, and so only B is flying straight, so it's going to make its way through the quadrupole and go on to hit the detector. But you can change the voltage, you can change the radio frequency, so you can make everything at some point fly straight. So you can change the conditions of the quadrupole to make whichever ion is of interest to fly straight and exit the quadrupole and hit the detector. So you can examine the entire mass range extremely fast just by scanning through different voltages, frequencies, and you can do that in the order of seconds. So you can analyze the entire mass range in a second. So a quadrupole mass analyzer is much cheaper and smaller than a magnetic sector mass analyzer. Okay, so that's basically probably most of what I want to say about mass spec. I may make another video and talk a little bit about fragmentation, but that just gives you a little bit of flavor for the different types of ways to get molecules ionized, and there are other ways as well, but those are some of the more common and popular ways, and a couple of different ways that you can separate your molecules out based on mass with different mass analyzers. Okay.